everyone. In this video, I'm going to tag our work ADV-BCT. Our code and paper are available in the web page. Traditional model upgrade requires maintaining both the new and old models, as well as the new and old database. By backward compatibility, the new model upgrade process only needs to maintain the new service and the old database. The backward compatible learning has two goals: to keep features consistent between two models to save time and resource, and do not sacrifice the retrieval performance of the new model. To achieve those goals, we propose ADV-BCT. ADV-BCT utilize the adversarial learning to minimize the gap between two feature spaces and propose an elastic boundary constraint. Our method outperforms other four methods in most allocation types. Now I will introduce the background of backward compatible learning. The task is to ensure the compatibility of embedding representations between models. The new model can directly replace the old one, and the embeddings of images in stock can be updated on the fly. Figure 1 shows the process of the compatible upgrade. Existing works can be divided into two categories: point-to-point based methods and point-to-set based methods. P2P methods constrain old embeddings and new embeddings. P2S constrain older class centers and new embeddings. Our approach can be divided into three modules. A classification module is to ensure the discrimination of new embeddings. Here we use cross-entropy loss. The adversarial compatible module is the discriminator to minimize the gap between two embedding spaces of two models. When implemented, we refer to GIL in domain adaptation. The boundary-aware compatible module is used to balance disparity and compatibility. Next, I will provide a detailed explanation of the boundary-aware compatible module. I want to explain why we use P2S constraint instead of P2P constraint. If compatible, the distance between positive embedding pairs from the new and old models should be smaller than the distance between negative embedding pairs from the new and old models, as well as the distance between negative embedding pairs from the new model. Applied to all pairs of examples, P2P is influenced by outliers. And according to the triangle inequality, P2P constraint can be bounded by P2S constraint, which won't be influenced by outliers heavily. Why do we use an elastic boundary? Simply, we can constrain the P2S distance by the maximum distance of classes. However, the corner cases and outliers will make the distribution looser, which leads to a larger maximum distance. Therefore, we control the boundary distance by using a learnable parameter between 0 and 1, namely elastic boundary. Considering the common scenarios of model upgrades, we have divided them into four allocation types. All methods are trained on the dataset GLDV2 and tested on R Paris, R Oxford, and the GLDV2 test. We adopted three metrics to evaluate the disparity and compatibility of models, and we proposed the p-beta score, which is the harmonic mean of compatibility and disparity. We implemented four methods, including the ADV-BCT. We got the compatible training benchmark testing on 5 methods. From the table, we can find that the ADV-BCT achieves the state-of-the-art in most allocation types. We also did some evaluation studies. We compared different components in extended data and extended class. From the table, we can find that combined with adversarial module and elastic boundary module, we got better results. Another interesting phenomenon is that the adversarial loss can accelerate convergence as shown in the figure. In this paper, we introduced the backward-compatible learning method ADVBCT to better ensure compatibility. We designed the adversarial and boundary-aware compatible modules. Adversarial compatible modules aims to pull the embedding distributions of the old and new modules close. Boundary-aware compatible module is used to obtain a suitable boundary to constrain distance relationship between the old and new embeddings. We establish a comprehensive benchmark for subsequent researchers to handily contribute to the field. That concludes all the content of this video. Thank you for watching.